Hello. Yeah. So good evening to everyone. So we will be waiting for more like 2 minutes more, and then we will be starting with our today's session. Okay. Let others come also. Okay. So we'll start with today's session, and uh, so welcome to the week two live session of electrical measurements and electronic instruments. So we solved lots of questions last week, and today also we will be doing the same. So I have prepared some questions we will be solving throughout the session. And before going to the questions, I would like to ask if you have any doubts, you can ask me now also, or you can ask me like anywhere. You can interrupt me in the session, and then also you can ask. So whenever you feel okay to ask. Okay. So yeah. So I think the last date for submission of the assignment is I think tomorrow. But yeah, so I think you would have done that assignment. So we'll just see what we learned in week two. So we talked about emitters and how we can we can see like what will be the internations of the emitter, like to have the lowest loading effect. And then we saw multi-range emitters, and then we saw two types of multi-range emitters. And then in which like one of that was make before break switch, which really helped in solving an issue of overloading of the emitter. Then we talked about voltmeters and range extensions in voltmeter. We did some questions also in the last week, like live session for that. Then we talked about ohm meter, how we can realize ohm meters from that, and some desirable conditions for ohm meters. Then we talked about rectifier-based voltmeters and ammeters and how we calibrate them, and we'll be solving some questions based on that, some good questions based on that. And full wave rectifier-based and half bridge also, half bridge rectifier-based questions also we solved. Like we saw in this week two. And then we talked about four terminal resistance thing. And yeah, so I think that was for week two. And based on those, we'll be solving some of the questions. So before diving into the question solving session, I'll first if you have I think pen copy or something, so you can write this table. This table will be really useful, not for only this course. It will be used for your, it can be used for your entire for analog electronics also. Uh, this table can be used. And yeah, so this is basically the average and the RMS values of different basic signals which you encounter while you're encountering your this electrical courses or in your electrical practicals, electrical and electronics practicals. So and these are important because it is good practice to know the the how these are derived, but actually after derivation, if you know the basic thing, so it is good, then you should know that thing on your tips. Like if you know the direct formula, you can apply in many questions without consuming a lot of time. Okay, so I will start with basic sinusoidal waveform. I'll try to like write properly this time, because yeah, so that you can understand. So so you can write down this table, you can note down this table. So average and RMS values of these basic signals. Okay, so for sinusoidal, average is full, if you talk about this, so it will be having an average of 2 Vm by pi, and RMS will be Vm by root 2. If we have half sinusoidal, okay, then we have Vm by pi as average and Vm by 2 as RMS. This is 1, 2, 3. If we have a square wave or a rectangular wave, okay, having both equal time periods, let's say, then we have average is Vm and the RMS also remains Vm in this case. For our fourth case, if we have half square wave, so this is full time period. Okay, so then it will be Vm by 2 average value, and this will be Vm by root 2. Okay, then if we have a triangular wave like this, so this is basically the time period of every wave we are talking about. So yeah, so this will be having Vm by 2 and Vm by root 3. So you can, it can be a homework for you, you can derive all the average and RMS values. If your answer is differing from any of the values, then let me know, we can together solve in the live session. And because I may also commit some mistake. And if another signal is half triangular wave, okay, this is full time period, so this will be having Vm by, or let's say, if it is not high half, we can generalize this as, this is t naught, let's say, for any t naught time period. Okay, if for any t naught time period and we have full time period as t, then the average value and RMS value, so average will be Vm t naught for the time period which is, it is like having that signal, and divided by 2t. Okay, this is the average value, and RMS will be Vm under root of t naught 3t. Okay, so if this is a half, like this is for t naught is for half time period, then this will become 1 by 6 root 2 for RMS, and this will be 1 Vm by 4, and RMS will be Vm by, so you can, this is a generalized formula for triangular waves. Then we have for seesaw waves, full seesaw waves like this, we have Vm by 2 and Vm by root 3. So normally the triangular and the seesaw waves, they have both have like the same average and RMS value. So you can remember like this also. And if we say generalize seesaw waves for t naught time period, the full time period was t, so it will be Vm t naught divided by 2t. Yeah, so Vm under root t naught divided by 3t. Okay, so just I'll give you some time to note this table, and because this will be useful for today's session also, and in general also, like you should know, okay, these are the basic average and RMS values of these quantities. And yeah, so you can take help of this for solving today's questions, and in like future also. One more thing I will like to add. So in especially in measurements questions, you can in not only in measurement questions, but in these half wave rectifiers and full wave rectifier questions, you can encounter this term form factor, and this is very common term which we use when we are dealing with AC signals. So form factor is basically RMS value of that signal divided by the average value of that signal. Okay, so yeah, just note down and then we will start with so I will solve some of the similar questions which can help you in solving your assignment questions, and then we will be solving some extra questions which can help you with this subject as well as your competitive exams also. Okay, or you can, yeah, so just write it down. I'll wait for 1 minute or 2 minutes. Yeah, then we will proceed. So okay, so now we will be solving some of the similar so I will not be like solving complete assignment questions because these were the previous year questions, but these are related to your assignments which you are solving right now, but the values are different but the concept is same, so I will give you hints for that, and yeah, we'll see. So I think you have noted down that formulas. So you can say, okay, this looks similar. The values are changing, but I will just give you a hint, okay, how you solve this. So first question, as it said, so yeah, so you had to solve like you had to solve. So what are the Rx, Ra, and Rv values for this question? So if you see the last circuit, then it we are having voltmeter reading is 500 volts and ammeter reading is zero point 0.5 amperes. And if we see this can be seen as, so we have, yeah, so RA, so we have ammeter reading we have. So let's say this was the current IA that is being mentioned here. This is IA. Okay, and we have the voltage drop across this, so this can be visualized as an PMMC meter with a series multiplier that is having RB value, and it is having a voltage drop of 500 volts which is mentioned here. Okay, so this like this you have to think. So for this like wait, let me admit, yeah, so for this so you have zero point 0.5 current flowing through this, and then you have two resistances in this. One resistance is here also, this Ra. Okay, that is the ammeter resistance Ra, plus we have this voltmeter resistance Rv, which is equal to actually the total voltage drop. Okay, so we have one equation from this thing. Similarly, we can go for this, as in this we can again like solve we can again solve one more, we can have one more equation for this. So if we have a current, let's say this was IA, let's say this is I prime, this is I double prime. So we know this voltage, so I'm only giving hints for these questions. So we know this voltage and I prime Rx, so we can write like this: I prime Rx equals to I double prime RV. Okay, and for this question we have voltmeter reading, so this whole thing is 165 volts. Okay, and we have this IA as 2 ampere, so we can either like remove I double prime by 2 minus I prime, or we can remove I prime accordingly. So we'll reduce one variable. So after that we can solve this also. Okay, so if you have any doubts you can just ask me, but just I'm going through these questions like fastly because we have other questions to solve. Similarly, in this, if we have RV, so we have again voltmeter readings and we have ammeter. So now this current I, this is having current is in this branch 5 amperes, and we have voltage of whole this branch. So 500 is basically the voltage drop across 5. This is the current RA plus RX. Okay, so this is 500. This is the complete voltage drop across this part. So we will be having one more equation from this. So we'll have three equations like this, and we can solve these questions. So it's a easy question. So these three questions were based on this. So after this, we have another question in which the positions of one, like this switch is being changed from 1 to 3. So if we are changing 1 to 3, just simply, if let's say switch is in this position 1, then we have R1 here, and in parallel we have RM, and then we have in with that R2 and R3 also. Okay, so we have like this for position 1, if this is position 1. For position 2, this is RM. We will be having in parallel R1 and R2, then we will be having R3 like this. So this will be like this, these are two terminals. So this is position 2, and similarly you can go for position 3. So this is a basic KVL KCL you can apply in this and then solve this. So this is also a simple question. Then okay, so all, yeah. So now last part, a voltmeter is prepared with a PMMC instrument, series resistance, and ideal diode in series. The voltmeter gives full scale deflection for 5 volt DC voltage while measuring AC voltage. So they have the deflection with us. So in this we had, yeah, so we had something like this. So we have a PMMC instrument, okay, a series resistance with this, with it, and an ideal diode in series. So basically this will only uh, get the value for half wave of the cycle. That's why this diode, that's what this diode is, uh, diodes working is here in this case. So this is saying the voltmeter gives, so this says the voltmeter gives full scale deflection for 5 volt DC voltage while measuring an AC voltage. With this voltmeter, 60% deflection is observed. So we have the deflection of 60%. Okay, the frequency of the AC voltage is known to be 60 hertz. So they are given the frequency also. So estimate the amplitude. They are asking to estimate the amplitude of the AC voltage if the AC voltage is a perfect square wave. So if we have given a perfect square wave, so what will be the final output of this? So first thing to keep in mind that since we are having a diode in our case, so this will be half wave rectified. So we won't be having the negative cycle of this, and we'll be having some signal like this. Okay, so yeah. So now we have yeah, okay. So V average, so 60% deflection. Okay, so 5 volt was for full scale. So for 60% deflection, we will be having 3 volts as the reading. Okay, and the average value, because PMMC measures the average value. So average value of this half wave, half square wave is what, as I told you in that table also. So you can check that table. It is like Vm by 2, which is equals to 3. So we can get Vm equals to 6 volts. Okay, so they are asking for the amplitude of the AC voltage, so we can get it like this. So that's why that is the importance of remembering all those average and RMS values of the signal. And so you can directly say, okay, this is the Vm by 2, the average value of this half wave signal, and we can directly get the answer for this. So similarly for triangular wave and sinusoidal wave, you can solve these questions. Okay, so I think you will not be having any doubt, because in these assignment questions, so these I have given you the hints for that. So now we will be moving towards some extra questions, so which I will be expecting you to solve along with me. Okay, so that we can have a good interaction, and yeah, we will be solving together. So this is the first question. If it is not clear, I will read it for you, and I will be so yeah, it will be good if you solve with me. So I will be giving you some time. Then accordingly, you can post your answers in the chat box, and if you can switch on your mic also to give the answer, whichever way. Okay. So the first question is, ammeter voltmeter method is employed to measure the resistance of resistance R. So we have this resistance R, okay. From among the circuits shown below, the least erroneous results are obtained by adopting. So they are asking which will among these two, which will be having the least erroneous results. So try to remember the lecture sessions which you had, which you saw in the last week, and just try to give the answer for this. So I will be giving you some time, 2 3 minutes. So I think this is easy, but yeah, you can give the answer. So yeah, you can write in the chat box. So let's say we have ammeter resistance. So it's like this is our ammeter resistance RA. If we are replacing them with their resistances, this is RV, and this is R which we are trying to measure. So this is the first configuration, figure 1. And in second configuration, we have one RV resistance in parallel with this. Then we have RA, and then we have this resistance R. So remember what normally the resistance of an ammeter is, what normally the resistance of a voltmeter is. So accordingly, you don't have to remember any formula. Just based on logic also you can answer this question. Any answers for this? So first option is saying circuit 1 for low resistance and circuit 2 for high resistance. So so the options are, if this R was high, if R was high, then which configuration? Then configuration is what? Okay. And another is, if R was low, then which configuration? So simply, if you just go by logic, so just remember, ra, the ammeter resistance is very low. Normally it's very low because we add one shunt in, and normally the coil resistance of the PMMC meter is very low, and we also add a very low shunt resistance in parallel to this. So normally ra, the ammeter resistance, is very low, the equivalent resistance. So let's say this is very low, okay. And normally the voltmeter resistance is very high because we add one series resistance in series with the coil resistance. So normally this RB is high. So let's say if a current was going from here, I, so this ammeter measured that I current. So since RB, so if let's say this was R was very high, okay, we are measuring a high resistance, let's say. So what will happen? So this R, if this is high, so this will be in comparison, like we can say that RB and R, if they are like almost same in nature, in same ranges, then we can say that the current which is being diverted here and here, so they will be having, so this I prime will be having quite a, like, it will be having large amount of its part in this I, okay. But let's say if this R was low, okay, so the most of the current will be flowing from this branch, because this RV is very high in comparison to R. So let's say if RV was very high in comparison to R in this figure 1, so what will happen? Most of the current will flow through this, and we needed that only, like the most of the current should flow from the resistance for which we have to measure that. So that means if this R is very low in comparison to RV, then we will be having, then this is a good configuration to solve for low value of resistances. if we see this thing. Yeah, wait, someone is coming. Yeah. So if we see another, if we see the second configuration, so what this configuration is saying, let's say we have this I current, it got diverted into I prime and I double prime. Okay, now this voltmeter is measuring the voltage across this branch, which is consisting of RA and R. So let's say if R was very high in value, so this whole resistance branch is R plus RA. So what will happen? This RA is very low in comparison to R. That is, R is very low in comparison to RA. Okay, R is very low in comparison to RA. So this will be equivalent to R plus RA will be equivalent to approximately what? R. So this will be having very less effect on this whole branch. Okay, yeah. So I just cleared that out to remove that clumsiness. Hmm. So did you get my point? If no, you can ask. If no, you can just write no again in that chat box. I will just tell you again. Uh, if yes, then give the answer. I think now you can give the answer for this. It's very simple. Okay, yeah, you can switch on your mic and then ask. Yeah, Pankaj. Yeah, you have some doubt. If no, okay. So the answer for this is the first part, because circuit I for low resistance. So as I said, circuit I is having low resistance. If this R is having low resistance, that means this RV, because this is in parallel with R. So RV parallel R, this will be approximately equal to what? R. So this will be like, so this will be good. So this configuration is good for what? Low value of R, low value of resistance R. Because in parallel combination, the resultant is the lowest value of the both the resistances. Okay. And circuit 2 for high resistances. So in this circuit, if RA plus R is very high, so in this RA plus R, if this R is very high, so this will be approximately equal to R. So this RA will be having less loading on this R. So did you? So this is the reasoning for this. If you didn't get, so you can ask me again. If you
Okay,
got,
sir.
yes, yeah. You have any doubts? Okay, so yeah, Pankaj, you want to say something? Okay. Yeah, we'll move towards the next question.
Okay, sir.
Okay, yeah, thank you. So now next question is, a sinusoidal voltage of 230 volt RMS 50 hertz is connected to a rectifier type ammeter which do not follow the flow of current in one direction and offers a resistance of 30 ohm to flow of current in another direction. So just read the question properly, take your time and solve this. I will draw the diagram for this. So how this thing is looking like. So we have a sinusoidal voltage which is having 230 volt RMS 50 hertz frequency is connected to a rectifier type ammeter which do not allow the flow of current in one direction. So they are saying they have rectified this ammeter by, and how they can do this to stop the flow of, do not allow this flow of current in one direction by using one diode. Okay, and offers a resistance, and this is having a resistance of 30 ohms, coil resistance we can say, in an offers a resistance of 30 ohm to flow of current in another direction, current recorded by the ammeter is. So we have this PMMC meter here. So this question something, the circuit looks something like this. Okay, so now you have to, so they are asking the current recorded by the ammeter is. So first of all, just I will say, so we inputted a sinusoidal signal from here, from this point into the circuit, into this what we had this as a measurement equipment. So this whole thing is consist of our meter which is measuring our signal. So our signal looks something like this. So it is having 230 volt RMS value. That means its peak is 230 root 2. Okay, that is fine. I think sinusoidal signal having peak of 230 root 2 because this is an RMS. VM by root 2, so root 2 goes there. Okay, and it is having a frequency of 50 hertz. Now it is being given to a meter, and the meter outputs a waveform of what? It outputs a waveform like this. Okay, why? Because in one direction this diode will not allow the current to flow, so we'll only be having a half wave rectified signal output. So this is like this is VM. So now they are asking for the current recorded by the emitter. Now I think this is simple. So we have a waveform like this, and you have to solve the current in this circuit. So current basic formula is V by R. I think now you can solve this and you can tell me what is the answer. And one more thing to keep in mind, if so this emitter calculates the average value of the signal. So the average value of the signal will be what? So this V output, so it is calculating the average. So this will be for half wave sinusoidal signal. Just look at the table and see what is the average value of this half wave sinusoidal signal. So it is Vm by pi. Okay, you can look at the table which I just wrote in the starting. So this is Vm by pi. Okay, so Vm by pi, this is the average value. So now we will have I average. So this, according to this equation, V average by what is our the total resistance of this whole circuit, that is 30. So V average will be Vm by 30 pi. Okay. So Vm is for, that is 230 root 2. Okay. Divided by 30 pi. So this will be 3.45 amperes. Any doubts in this? You can just say yes or no. If you don't have any doubts, you can say yes in the chat box. And if you have doubts, you can say no and you can ask me. If you will say nothing, then I will think that you have no doubts in this question, or you are still thinking. Is this fine? I think this is fine. So we will okay. Thank you. At least some yes is fine for me. Okay, so we will move to the next question. So yeah, just look at this and think. So I will draw the diagram for you. So first I will read the question for you. Okay. A half wave rectifier type AC voltmeter consists of a series resistance RS. So just slowly read the full question. A diode with a forward resistance of 50 ohm. So they are saying there is a diode with a resistance of forward resistance of 50 ohm, and PMMC instrument shown in the figure. Okay, I will draw the figure for you. No worries. Uh, yeah. So this was. Did I miss? Okay, no. So okay, I will draw the figure for you. So this figure is simple. We have a diode with a resistance of RS, which is having a forward resistance of 50 ohms. So it looks like something like this. A half-wave rectifier type AC voltmeter consists of series resistance RS, and it is also having a series resistance of RS, which is equals to RS. Okay, they haven't given the value of this RS. Okay, I doubt the forward resistance and PMMC instrument. We have this like shown in the figure. The internal resistance is 100 ohms, so this is having an internal resistance of 100 ohm, that we know, that is okay. Deductible. And full scale deflection is produced by a DC current of, so this is having an I full scale of 2 milliamperes. The value RS required to obtain full-scale deflection with an AC voltage of 20 volt RMS. So now they are asking for this value. What will be this value required to obtain full-scale deflection with an AC voltage? So now they have given an AC voltage of 20 volt RMS from this side. Okay, applied to the input terminal. So now they are asking for this RS value. What will be this RS value which will give this full-scale deflection? 2 milliampere of this. So remember, a PMMC meter calculates always calculates the average value of the signal. So when they mention this DC current, when they mention this that it produces a 2 milliampere of DC current, that means this is the average current. Okay, so this is 2 milliamperes. This is the average current, which average full scale current, which is being measured by this PMMC instrument. So now again, if you reduce the question, so let's say we had so we had applied, so we applied I think AC voltage. So let's say this was a sinusoidal wave of 20 volt RMS. So its peak was what, 20 root 2. Okay, this much is fine. It was being inputted to this meter. Okay, this meter. So this is a complete meter. So this thing is a complete meter. So this signal we have fed to this meter, and then this meter will first of all, so let's go step by step. This diode, what this diode is doing, this diode is basically making this signal a half wave rectified signal. So for positive cycle it will allow the signal, for negative it will not allow the signal. Another thing being done in the meter itself, so this is all being done in the meter. Okay, so there is, so this diode made this half wave rectified, and then this PMMC meter is calculating the average value of this signal obtained after the diode. So basically we are calculating the average of this signal by this PMMC meter. Okay, I think if this is fine, so let's write the basic equation for this circuit. And one more thing, this RS, if we added this RS, so this RS basically, as you studied in your previous weeks also, so multiplier resistance is used to amplify or to extend the range of the voltmeter. Okay, so that's why this RS is being used here. Rest is their internal properties. This 50 ohm is the internal property of your diode. This 100 ohm is the internal property of that PMMC meter. Okay, this much. If this is clear, then we can proceed further. So how we will proceed further? So this I average we know. So they are asking that what will be the RS value if we have to produce full scale deflection. So full scale deflection is I average. So that means in this full circuit, there will be current of equivalent to I average. Okay, I average will be flowing, or we can say, yeah, I average will be flowing. So this I average will be equal to what? The voltage, whatever the input voltage we have here, the average of that, because we are dealing in average. Remember, we are dealing in average. So we input average divided by the total resistance of the circuit. Okay, this is simple. This is basically Ohm's law. So this we will be having RS, one multiplier resistance, plus we will be having the diode resistance in when, because they said for forward when it is forward bias, so it is having 50 ohm resistance. So we have a diode resistance. Let's say I'm writing that as RD plus the coil resistance RC. Okay, this is the thing. So we have 2 milliampere as this I average current. We this is the average value of the voltage which is being given to this PMMC meter. Okay, and this is RS we don't know, plus this is 50 plus this is 100. Okay, now the question is, what is this the average value of this voltage? Actually this is not input average, this is the output. This is basically the voltage which is being given to this thing, this PMMC meter. We output average. So what we have as output, we have output across this PMMC meter as this half wave rectified sinusoidal signal. So what is the average value of a half wave rectified sinusoidal signal? It is basically Vm by pi. Just look into that table and you will get to know, okay, it is Vm by pi. That's why that table is this much important. Okay, so this is the average value for half wave rectified sinusoidal signal, sine signal, Vm by pi. Okay, so now we have Vm by pi, and what is the Vm value we can have? So this was the peak value of this, that is the peak value of the signal. So this will be 20 root 2 divided by pi. Okay, so this we can give into this formula. So this will be 2 milli equals to 20 root 2 by pi divided by rs plus 150. Okay, and then we can solve this rs value. So this rs will be around rs will be around so I don't want to solve completely. Yeah, I think it is around 4.3 something. Okay, you can solve this. What will be the rs? Just let me know what is the rs. Okay, so this is one thing. So we will again just go through this thing. So what we did, first of all, again we will just read the question slowly. Okay, a half wave rectified type AC voltmeter. So this AC voltmeter is rectifying the signal. It is a half wave rectifier signal and consists of series resistance RS. So this RS, they introduced this. Why? Because they had to increase the range of this voltmeter. That's why they increased that. That's why they introduced this series resistance RS. So till now this fine. So we have a half wave rectifier AC voltmeter which is consisting of series resistance RS. So now they're saying a diode with a forward resistance of 50 ohm and PMMC instrument, okay, as shown in this figure. So how they made this half wave rectified thing? They made this with the help of a diode. They need something to make that signal half wave rectified. So normally we use diode for that case. So in this case also they use one diode which was having a 50 ohm forward bias resistance, this 50 ohm, and this was being connected in series with this PMMC meter, so that to make the signal half wave rectified. Okay, so till this point I think this is fine. Now the next thing is, now they are saying more that the internal resistance is 100 ohms. So internal resistance of this PMMC meter is 100 ohms, and full scale deflection is produced by a DC current of 2 milliampere. So when they said DC, that means the average value of the current. So that means this PMMC meter is calculating the average value, means this is showing the average value. Okay, 2 milliampere, that is 2 milliampere. So this is 2 milliampere. Okay, so this full scale is 2 milliampere, which is the average value of this, what is being measured by the PMMC instrument. Now, so they are asking, so what will be the value of rs required to obtain full scale deflection? So now they are saying, if we give a voltage of 20 volt rms, so 20 volt rms value, if we input it to this circuit, to this PMMC meter, then so what should we keep this rs value, so that the output, the PMMC meter will show full scale deflection. Okay, so first of all, we first of all we analyze that, okay, PMMC meter looks like this. We have a PMMC meter. This is PMMC. It is having an internal coil, 100 ohms, having a half wave rectified it can half wave rectified any signal. Why? Because it is having a diode which is having a resistance of 50 ohms. Okay, then we added one rs, that is a multiplier resistance, to increase the range of this meter. Okay, then they are asking to that we need 20 volt rms value. If we input into the signal in the meter, then what will be the full scale, and if it is showing the full scale deflection, then what will the value of rs? So if we have the clarity of the question, then we can proceed like this. So this was the input signal. This was being half wave rectified by this diode. Okay, and then the PMMC meter is giving this, this signal. The PMMC meter is giving a half wave, the average value of this half wave rectified signal. Okay, so now we have I average, that is the full scale deflection, is equals to the output voltage which is being observed at the PMMC meter divided by the total resistance of the circuit. So we have I average as 2 milli and V output of average. So this is the output signal. So the average value of this output signal is what? It is basically half, as given in the table. This is Vm by pi for half wave sinusoidal signal, and we have Vm value by the quotient itself. So this we can substitute in this formula, and then we can get Rs. Okay, is this okay to you? Somewhat clarity you got, or like nothing you got? You can say yes or no. Okay. Okay. Somewhat. Okay. You got the clarity, or like somewhat. You can just go through again this explanation. Okay. Yes. Okay. So we have two yes. So I will assume at least you have got some clarity on this type of questions. And if yes, then we will move forward. Okay. So now this is a simple question to relieve you from difficult questions, and I need answer from your side. So please give me the answer. So inductance of certain MI ammeter is this, and the control spring torque. So I will also write the question for you. K theta equals to half I square dl by dt d theta. So they are asking the reflection of the pointer in radian when it carries a current of 6 ampere. Now I need the answer from you for this question. You can write in the chat box. Yeah, I think the formula is right. Yeah. Any answers? Okay, I will start solving. Meanwhile, you can answer. So, so this is very simple. We have this control spring torque is what? K equals to 35 micro nanometer per radian. And when you're solving anything, just look for the what will the units. Okay, the units of the things which are given in the question. Okay, so this is K, and we have we need deflection. Okay, we need theta. So theta equals to half K I square dl by d theta. Okay, so now this is simple. We have L equals to 30 plus 2 theta minus theta square by 18 micro henry. Okay, so we need dl by d theta, that is the differentiation. I think you have learned this differentiation, dl by d theta, which is what? So for a constant term it is 0. This is 2 minus 2 theta by 18 microhenry. This is 9. Okay, so this is 2 minus theta by 9 microhenry. Yeah. So if we substitute this thing in this, and K value is what? 35 micro. We have I as 6 square. We have this as 2 minus theta by 9 micro. We have theta. So I think this is simple. We can solve the value of theta from here. Okay. So I think this was the gate question for one of the uh, any of them. I think some previous year gate question. Yeah. Uh, so I think this is okay. If we can if this is fine, we can go to the next question. Okay, I think yeah, this should be fine. Then yeah, the next question. So I just the diodes were different in this, so it were wrong. So I just corrected that. So I think the question is in front of you. So just you have to write the. So the first question is the voltmeter is PMMC. So let's say this was PMMC. Then the reading shown is. So we have this. So it is repeating after this. Okay. So we have the square. Then we have a dead zone. Then we have again that same period repeating. So this is the full time period. So based on that, what is the reading shown? Okay. So as I said, as I gave you the formulas for those basic signals, but just keep in mind for this, I think this is since having a dead zone also. This those formulas cannot be applied directly here. So just that the just don't apply blindly the shortcuts or the remembered formulas. You should know when you have to apply that. Okay. So yeah. So go with it and then just tell me what is the answer. I'll give you some names. Okay. I think yeah, you should solve it. Is the nice habit to solve these things because it will help you engage in this session. So if PMMC is there, so we will be it will be calculating the average value of the signal. So you just have to calculate the average value of this, and if this is MI, then you have to calculate the RMS value. Okay, and yeah. So for average value, the formula is 1 upon time period is 8 in this case, integration over 0 to 2 for first wave 2 dt plus 2 to 4 minus 2 dt plus 0. Okay, so this will be 0. So because these will be having same and opposite values, and you will get 0 for this. Okay, so this is 0 volts. uh, is it 0? Oh no 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 no. This is yeah. So this will be not. This will not be zero. I mistake. I did the mistake. Wait. Since we are having full wave rectifier, so it so we let's make the so let's use that thing. Sorry for that. So this will not be zero. So first of all, how the signal will be looking like? We'll see that. So since we have oh man, yeah. Since we have a full four diodes, so it will make this thing look like this. Okay, this and zero. Okay, this will be looking like, so all the positive, all the negative cycle wave will be going to the moving towards the positive side. Okay, so this is 2, this is 0 2 4 8. I think now you can solve this. Now it is repeating from this part on. So now the average will be what? Average will be equals to 1 by 8 again. 0 to 4, it will be 2 dt, rest is 0, like this. So this will be 1 by 8. Okay, and this will be what? 2 t, so it will be 4. So this will be 1 volt. So this will not be 0, this will be 1 volt. And what will be the mi instrument measurement? This RMS, this is equals to what? So RMS square, if we take the whole time period 1 by 8, the waveform is same, 1 by 8 integration 0 to 4 2 square dt plus 0, like this. Okay, so this will be 1 by 8, 4 into 4, 2. Okay, so this will be root 2. We'll have this as the answer. Simple. Okay. Any doubts? Any doubts in this question? I think no. No, sir. Okay. Okay. So we'll move to the next question. Okay. Uh, okay. Empty space. Yeah. Next question. This is also a gate question. Just try to answer. It's a easy question. Very easy. Just logic. If you know the functioning of diode, then you can answer this. So if those who don't know the functioning of diode, just I will let you know. So if this voltage is higher, let's say this V1, this is V2. So if this voltage is higher than V1 is greater than V2, then this, for an ideal diode, this will be a short circuited. But if V1 is less than V2, then this will be open circuited. Simple diode. Okay. So now you can answer this. Can anybody write the answer in the chat box? Any guesses? So remember, this is a DC signal which is being given here, and it will be having polarity like this. It will be flowing like this. So they are asking what will be the value of this current I. It's very simple. So the answer to this question is, if you had the answer and you didn't, you were shy to write the answer in the chat box. So just to tell you, the answer is 0 milliampere, because one diode will be, this will be on, but this will remain off. Okay, so the I will be 0 in this case. Hmm? I think this was easy, just like how the diodes are functioned. Okay, now the next question. So read the question carefully and then try to figure it out how you will be solving this. So there is a setup, there is a figure. This is used to measure resistance R. So they are using this circuit to measure the resistance R. Okay. The ammeter and voltmeter resistance is R. So this is also a gate question. The ammeter and voltmeter resistance is R. So this is having 0.01 ohm and this is having 2000 ohm. Their readings are 2 ampere and 180 volts. So this current, the readings are, this is 2 amperes and the voltage across this is 180 volts, giving a measured resistance of 90 ohms. So R measured equals to 90 ohms. The percentage error in the measurement is. So when they said percentage error, that means what they have measured is not actually the true value of the resistance R. One thing. Second thing, second thing that should come in your mind is why it is not the true value, true measured value of the resistance R. If you see the figure correctly, then what is happening? We had, let's say this was having, it is having R resistance, so this 2 ampere, so the current might be, let's say the current which was here, so this current will not be equal to 2 ampere. Okay, so if we tell R true, that will be like, So whatever current, so this will be, and let's say this current we named as I prime. So voltage we know across this resistance, that is V. That is fine. Voltage is fine, but the current is I prime. But what is being measured? The measurement done here is this one. So this is V and this is I. So this I is this current I, okay, which is being recorded by the ammeter. So this is V by I. So that's why we are getting this. This is equals to 90 ohms, but we need this. So that's why there, okay, 4.5%. Okay, we have one answer. Okay, any other answers? But I think yeah, 4.5 is correct. So yeah, so I think you got my point. The question is straightforward. So that's why we need the percentage error. So what will be R true? So you can simply solve like this. This is, let's say, I double prime for those. For others, like so we have this thing. The voltage drop we know, that is 180, and we can have this current as, or we can have this current as, in this branch, this current I double prime into 2000. This will be 2 minus, that is the full current, minus I prime, that is the current through this, will be having 2000. Okay, 180. So the I prime will be, we can get I prime as 1.91. If we have I prime, then we can get the true value of this resistance, that is, or yeah, that is V by 1.91, that is 180 by 1.91, and it will be 94.24. So this is the true value, and this was the measured value of this resistance. Okay, so then the percentage error will be what? Simple, 2, or we can say measured value minus true value divided by true value into 100 percentage. Okay, so this was true value, this was measured value. So you can get the answer from this. Okay, so we'll move towards the next part. Yeah, just read this. This also kind of easy. This is also a great question. So a 1000 volt DC supply has two one core cables. As its positive and negative leads, their insulation resistance to earth are 4 mega ohms and 6 mega ohms. So they are saying, so this was one cable lead, this was another cable lead, and each is having resistance like 4 mega ohm and 6 mega ohm, okay, respectively. A voltmeter with resistance 50 kilo ohm. So this was having a resistance of 50 kilo ohm, is used to measure the insulation of the cable. So this is being used to measure this insulation. Okay, this 4 mega ohm resistance. So when connected between the positive core, this is positive core, and this was negative core, and this is earth. Okay, this is ground basically. The voltmeter reads. So what will be the actual voltmeter reading? So I think this is also very simple. This so we have this 4 mega ohm here. We have 50 kilo ohms here. Okay, and we have 6 mega ohms here, and we have a ground here, and we have a voltage drop of 1000 volts here. So just tell me what will be the answer. Is very easy. So we will be equals to 8 volts. Okay, we have one answer, 8 volts. Okay, any other answers? 8 volts is right. 8 volt is right. So for others it's simple. So V will be what? It will be so let's say I think you know this thing, like if we have a voltage source here, let's say V plus minus. Okay, if we have a voltage source here, then if we have two resistances R1 and R2, so the voltage across any of this, let's say voltage across R2 will be what? V into the resistance is R2 value divided by the total resistance of this branch R1 plus R2. Similarly, for voltage across R1, it will be V R1. So it will be V R1 plus R2. Okay. So this is like the voltage across R2, and this is high voltage across R1. So this is a nice way to remember this thing, so that you can apply this thing in many of the circuits. So similarly, you can apply in this circuit. So we have the voltage across whole of the branches for 1000 volts, and we need the voltage across this branch. That will be the equivalent resistance will be 4 mega parallel to 50 kilo divided by the resistance of total branch. Okay, 4 mega parallel to 50k plus 6 mega. Fine. So now you can solve this and you can get the answer. I think this was easy. Okay, if this is fine, then we'll move towards the next question. Again, a great question. So I think you take your time and then solve this. So the question is saying input impedance of the permanent magnet moving coil voltmeter is infinite. That means no current is flowing through this. That means this. Assuming that the diode shown in the figure below is ideal. Okay, so there is no voltage drop or internal resistance of that diode. The reading of the voltmeter in volts is. So they are saying the reading of the voltmeter in volts is. Just read the question and then answer. It's also very easy. So first of all, you will have to think. Okay, we have a sine wave. This was an input sine wave. Okay, so this is an input sine wave, and what will happen in positive cycle? So positive cycle. So this will be what plus this will be minus. So this will be shorted. If this will be shorted, then this circuit will look like for positive cycle of the signal. Okay, so this will be shorted. We'll be having 100 kilo ohm, and we'll be having this voltmeter here, which is having this plus minus polarity. So if this branch is shorted, then the voltage across this voltmeter will be what? 0 volts. Okay, we have one answer, 4.4. Okay, any other answers? So meanwhile, yeah, I will get to that answer. So we have 0 volts across this for first half. So we gave this as input, and first half we got 0. What will be the second half answer, second half value? So it will be so for plus minus. So for the negative cycle, it will be like this one, and this will be now open circuited, this diode, because now we are moving like this. Okay, so this will be 100k. Now the current will be moving from 100k. Now voltmeter can read something. So we have 100k, we have 1k here. So what will be the value? Value will be V average, which is, and what we have to calculate the voltmeter readings are. So voltmeter readings will be what? V average will be equal to we have 14.14 is the peak value, 14.14. So divide by pi, that is the average of this. Okay. So yeah, basically this is equals to 100k into V average divide, because these are two resistances. Again we are using this thing, voltage divider thing, and if we solve this, so this is 100k plus 1k, V average into 100k. So this will be 100, 101, and V average will be what? This is output. This will be Vm by pi, because we have what we have across this is like a half wave rectified signal. So this will be this. So we have Vm as 14.14 root 2. Sorry, we have 14.14 divided by pi divided by 101 into 100. Okay, if we solve this, we'll get 4.4. So the answer was right. Any doubts in this question? The final the voltmeter which the signal which was being seen by the voltmeter was a half wave rectified signal like this, So that's why we, if we calculate, and PMMC meter every time it calculates the average value, so it will calculate the average value of this signal. And the average of this half wave rectified signal is Vm by pi. Okay, so that's why we use this V average as Vm by pi, and then we calculated this. Okay, if this is fine, we can, this is a good question. But you can solve this. This is also a great question. You can solve this. Yeah, you can solve this, and yeah, just try this. First read this and then see and visualize what is this saying. After 2 minutes I will at least draw the things which this, at least the question which is saying, and then you can think more. So but first of all, like, visualize yourself and just think what the question is trying to say. Okay. So slowly I will start with the question. So there are two emitters X and Y. Okay, we'll do like this. Okay, we have two emitters X and Y. So the resistances of them are 1.2 and 1.5. So one is having, so how we draw an emitter having a resistance like this. Okay, so this is having 1 point, so X is having 1.2 ohm resistance. So if we say resistance of an emitter, that is the coil resistance of that emitter. Okay, and this is having 1.5 ohms. Okay, and the full scale deflection is, for X is 150 milliampere, and for the Y is 250 milliampere. Till now it is okay. Now the next line with what it says, the ranges have been extended by connecting shunts. So now how to extend the range of an ammeter? By connecting shunts in there. So if we connect a shunt in this, like this, and another shunt in this here, so we can extend the range of this ammeters. So it will be, the ranges have been extended by connecting shunts so as to give the full scale deflection with 15 ampere. So for both these, so let's say we added one R1 here, another R2 here. Okay, for both the ammeters, the range have been increased to 15 amperes. So this is 15 amperes now, the full scale range. So we depict an ammeter like this. After extending the range, the full scale value will be 15 amperes. Okay, now the next, what the question is saying, the ammeters along with shunts, so along with these values, are connected in parallel, and then they placed in a circuit in which the total current flowing is 15 ampere. Okay, now visualize what it is trying to say. Let's say this whole thing I can represent it like this. This is an ammeter. This whole thing I can represent it like this: ammeter 1, ammeter 2. Okay, now what will happen? The question is saying it is being connected in parallel like this. If we expand this thing, this circuit, we will get ammeter 1 having an internal 1.2 ohm resistance with a shunt of R1. Okay, this is A1. Then we have another A2. This is let's say this was X, this was Y. Okay, and we have internal resistance of that as 1.5, and we have R2 as its shunt resistance. So if we expand this, it looks like this. Okay. Now the current in amperes indicated in ammeter X is. So now they are asking what will be this current Ix. Let's say this is Ix. If the total current flowing through this is the emitters along with shunts, these are, and the total current flowing is 15 ampere. That means now 15 ampere is flowing through this whole configuration. 15 ampere is flowing So what will be the current indicated in this x ammeter, that is this current ix. So this is the question saying. Now I think you can solve this easily. Just let me know what is the answer. So this question is really beautiful, I will say, because if you don't know this thing like how what is coil resistance, how shunts are given, and if they are connected in parallel, how they will look like, and all those stuffs, then I think yeah, it will be a little confusing. But I think if you get this, then it's fine. Then it's easy to solve. So you can also argue like this. They are asking the current in amperes indicated in ammeter X. So you can say, okay, there is a current here also. Let's say I prime. So why it's not Ix plus I prime? Why it is only Ix? Because what? Because it is not Ix plus I prime, because they are saying what is the current being indicated, and the deflection is only because of Ix, and that is what being indicated in this emitter X. So that's why they are asking only for this Ix. Okay, not asking for I prime. So just keep that also in mind. So if I skip the calculation part, and 10.13 we have one answer. Yeah, 10.13 is correct. So we have Ix as 10.13 amperes. Yeah. So yeah, this was this question. Any doubts in this? If no, then we'll move forward. Okay. Hmm. Now read this question carefully, and I will give you the answer for this, because this might be a new question for you. But I will tell you. Okay, so this type of questions can also these are kind of calibration type questions, and but these are like very good questions. So we'll see how to approach these type of questions. Okay. An electronic AC voltmeter consisting of full wave rectifier. You have already read about full wave rectifier. It has been told in this week two's lecture. Okay, and so they are saying just read this carefully. Electronic AC voltmeter. Okay, consist of so that consists of a full wave rectifier, average circuit, gives correct RMS value for square wave inputs. So what happens normally? What when we normally in practice, what happens? Uh, so let's say we have a full. So I for full wave rectifier, I will just draw this diamond. Okay, diode part you can draw yourself, just as a symbol, just for analogy kind of thing. Don't take it very seriously. So this is, let's say, a full wave rectifier. If we pass this thing from, if we pass the sinusoidal signal from this, and then we calculate this thing. Okay. Okay, just for the so what happens? So this is full wave rectifier, diodes for there inside that, and then we have a PMMC. So basically, it is like something you have seen this like this, okay? And so I'm just for the ease of understanding, I'm making it like this. So we have then PMMC meter. Hmm? Then it will, so what happens, so when if we give some signal in this, so it will rectify that signal first, and then this PMMC meter gives the average of that signal. So we get the average here. Okay, so what happens, so this, then we see that in the first week also we saw that, so there is a scale like this, and there is like this deflection. This happens, let's say if this was a voltmeter, then this is zero, then this is full scale deflection, something like this. Okay, so this will give average value. So what is whatever the average value of this is, then it will give the signals accordingly. But now here it is saying it gives correct RMS value. So now it is not giving average value, it is giving RMS value. So what they have done, they have changed this scale, this measuring scale, into RMS scale. RMS scale. So this is RMS scale. Okay. So this is 0 volts. So whatever the average value will be here is now being converted into RMS value of that signal, and then they are depicting that thing here. So this we say as a calibration thing. Okay, so instead of average, now the fine. So now this meter. So if you see a meter in your lab, and it is having something like it has something like this, huh? So if this is being calibrated into its RMS value, that means initially it was calculating the average, and then finally this signal is being outputted into RMS value of that signal. So this is being calibrated. This is what we say calibration. Now, when we say calibration, so this is RMS scale. So we can say calibrated into RMS scale means whatever average we got, we have converted that into RMS scale, RMS value of that signal. Now, when we say that this is being done for square wave inputs, so what they are trying to say, so they have made this instrument. So this is now a full instrument, and this is the display part of that instrument now. Okay, and this part is all being done internally into that meter, and this is finally after like some calculations they are like showing the scale as the RMS scale. But for which signal? So they are saying for square wave inputs. So what they are saying, if we give a square wave input like this to this signal, let's say from this side, then after this full wave rectification it will look like this. Okay, for one time period. Then this PMMC meter, what it will give, it will give the average value of this signal. And what is the average value of a full wave rectified square wave? It is Vm. Just look into that table, you will get to know, or you can derive also. It's very simple. If this is Vm, okay, this is Vm, the peak value of this was Vm. So we had a square wave input, we passed that into full wave rectifier circuit. We got a full wave rectified square wave which looks like this, and then this PMMC meter gave its average value. So the average value for square wave is Vm. So this is V average equals to Vm. Now what we have done, we have calibrated this instrument into RMS, its RMS scale. So what is the RMS of a square wave? RMS of a square wave is Vm itself. Okay. That also you can calculate, or I have given that table also, so no need to worry. So now the question is saying, so this calibration part, so this part is done according to the square wave input. So let's say if there was a square wave input into this meter, into this meter, okay, then the final output will be according to the RMS value of a square wave input. Now, when will the issues will arise? So, if instead of square wave we give a sinusoidal wave, then let's see what will happen. If we give a sinusoidal wave, let's say this is a sine wave. So, what will be the full wave rectified? So, again we are going step by step. So, full wave rectified signal will be like this. Okay, a full wave rectified sinusoidal signal. Now, the PMMC instrument, this PMMC instrument will give what? The average of that. So the average of this will be V average equals to 2 Vm by pi. Okay, so this is the standard formula for the average value of a full wave rectified sinusoidal signal. But now, what the RMS value would have been for this sinusoidal signal? So it is basically Vm by root 2, that you know. Vm by root 2 is the RMS value of a full wave rectified sinusoidal signal. But instead of that, what it will give something like this, because it is being calibrated according to the square wave input. So the RMS value, so instead of this, it will not give this, it will only give Vm. So 1 by root 2 times more value it will give to this. So this will be the measured value by this instrument instead of this. So this was true value. Instead of this, it will give this value. So there is some error in this. So this we say as a calibration error. Okay. Till now, is it okay with you? You can write okay. If okay, we will move further in this question. Just write in chat box okay, yes. If not, I will just give again this clarity on this. Till now, is it okay? Okay, okay. You have the answer also. We'll discuss the answer later. Okay. Uh, what about others? Is it okay? So what the question is saying? So for these type of questions or normally calibration, what is happening? Just once again, electronic AC voltmeter consists of a full wave rectifier, and there is an average circuit gives correct RMS value. Okay, for square wave inputs. So now what this fun statement is, for this first statement I again tell this. So there is a full wave rectifier circuit, then we have a PMMC meter, which is an averaging circuit. It gives the average output. it so the scale would look like, based on the average of that IPMMC instrument, will look like this. But instead of that, these people, what they did, they calibrated this average of the scale, the average output of the scale, into the RMS of that value. So whatever average they are getting, so they are converting that into the RMS values. So this RMS, whatever they are calculating, this is based on square wave inputs. So if we give us that, what does that mean? If we give a square wave input, the full wave rectifier will fully rectify it. Then PMC meter will give the average of that. Then according to the calibration of the square wave input, we will get the RMS of that as VM. So this VM is basically the the RMS value for square wave input. So if we have a sine wave, so what will happen if instead of square wave we give a sine wave? So let's give, if we give sine wave, we get a full wave rectified signal, and we get, based on PMMC, we get V average as 2 Vm by pi. But if we see that on the RMS scale, so this is the final RMS scale in this thing. If we see that, so then it should give Vm by root 2 value. But instead of that, it will give Vm. Why? Because it is being calibrated according to the square input as it is given in the question. Okay. So now this is the question. This is the core of the question. Now I'll just add one paper in this. Add. Okay. Okay. Yeah. Hmm. So now the next part. What the next part is saying. So it's reading for a 4 volt peak to peak sinusoidal input will be. Now it is asking. The question is asking. So what if we give a 4 volt peak to peak? When we say 4 volt peak to peak, it means 2 volt peak. So they are basically saying from one peak to another peak. So this is one peak, this is another peak. From this peak to this peak, it is having 4 volts. So what is the peak value of this signal? It is 2 volts. One thing. So now they are saying, if in this meter they gave the sinusoidal input, then which is having a 4 volt peak. So what will be the reading? So reading will be what? So we have, yeah. So we have this one, okay. So we gave this to a full wave rectifier. So then this signal was like this. Then we gave it to this. Then it will become like this. Then we had a PMMC meter. So it calculated its average value. So 2 Vm by pi. Till now it was okay. So after this there was a calibration. This is the average. Calibration done, and then what happened? We have RMS value, but this RMS value is based on the RMS of the square wave. Okay, so this was 2. We have Vm value. We have already that Vm value, 2 by 4. This is 4 by pi. So, but in case of square wave, what is V average? V average equals to Vm. Since this is being calibrated according to the square wave, so whatever the V average this PMC meter gave out, this RMS value will so this is equals to be RMS for a square. So this RMS scale will give that same exact value. So we had this average value. So the output we got is as 4 by pi. Okay. So what happened? PMMC meter calculated the RMS value, average value of the sinusoidal this thing. Okay, that was 2 Vm by pi. Then after that, after calibration, and this calibration was according to the square wave. So what happened? This average is equal to the Vm. Whatever the average is, we have that same as RMS value for a square wave input. So based on that, whatever average we got, the same thing it outputted at as it outputted as that same thing as the average of that signal. So that was 4 by pi. Okay. So this we got. So 4 by pi is 4 by pi. What is the value of 4 by pi? Is it 1? Half 4 by pi. It is correct. Okay. The answer is correct. Similarly, we will try this question also. Okay, just read the question. They have a rectifier type instrument, uses a bridge rectifier. They are using a bridge rectifier. If they are not mentioning half wave or full wave, just consider that to be a full wave rectifier, and has its scale calibrated in terms of RMS values. Okay, of a sine wave. Now what they are saying, so they had one full wave rectifier thing, then they have this PMMC meter. Okay, so here from where here the input signal is coming. Now this PMMC meter gave the average signal. Now it is being calibrated into its RMS value, but this calibration is done according to sine wave. Okay, so the average of this one of a sine wave is what? V average equals to whatever the peak value of that, 2 Vm by pi, and the RMS of the sine wave is given by Vm by root 2. So using these two relations, the final scale have been calibrated. Okay, which our customer is seeing on that box, on that voltmeter box. So this is being according to the sine wave. Now, now the question is saying if it indicates a voltage of 2.77 volts. So now it is saying that we got at this scale, at the display scale, we got a value of 2.77 volts. Okay, when measuring a voltage of triangular wave, so we gave a triangular wave signal here. Input signal was triangular wave. Not instead of sine wave, we are giving a triangular wave. The magnitude of percentage error will be. So what will happen? There will be error. As we discussed in the previous question, there will be error. I will tell you how. So this triangular wave, which is the input signal, it is being fed to the full wave rectifier. So this will become like this. Okay. Then what will happen? This PMMC instrument will calculate the average of that signal. It's nature. Okay. PMMC meter always calculates the average of any signal. So this will calculate the average. It will be calculating average as the average of this triangular wave. I will just write it like directly. It is Vm by 2, I think. Yeah, Vm by 2. Okay. So yeah, yeah, Vm by 2. So average of a triangular wave is Vm by 2. Now instead of Vm by 2, now we got the PMC meter output as Vm by 2. So now what will, so after this it showed this as 2.77 volts. Okay, but instead of this, if we are getting the, if we want to see the actual RMS value, the true value of a triangular wave, RMS value, the true value, the RMS in the RMS scale, it will be what? VRMS will be Vm by root 3. But instead of this, it showed according to this relation. Now you have to calculate what will be the error in this. Just think, but anyway, I will tell you that. So see what happens here. I'll just add one page. One. So now what happens? So simple. I think this part is now clear to you. So what is happening and what? But the only doubt may be what we have to do. So we have a 2.77 volt at display. So this is according to what? According to what calibration? According to sinusoidal calibration. It is written the RMS values of a sine wave. Okay, it is been calibrated in terms of sine wave, and it is showing RMS. Okay, so this will be equals to what? Vm by root 2. So this is being since it is being calibrated according to sine wave. So we have whatever we have as Vm by root 2 equals to 2.77. So we have Vm as 2.77 root 2. We got this thing. Now, if this was Vm, so what would have been the average of this? If we are, now we are going back. Now we are going back in this, like from here. Now we are going this, then we'll go like this. Okay, we are going moving back. So we had Vm. So what? So what average value this PMC meter would have read according to this? So that is according to 2 Vm by pi. Okay, V average. So this is 2.77 root 2 divided by pi. So this was the value which it would have it read, so that it will give like this value. So this is around 2.495. Now what is the actual true value of this triangular wave? True average value of triangular wave equals to, that is, V average of triangular wave is equals to Vm by what? It is Vm by 2. Okay, so this is the true value of the average of the this thing. So if we calculate, if we equate with this V average, so this, which is based on the according to the calibration of the instrument. This is sine wave calibration. So we have this average. So if this Vm by 2 is equals to 2.495, so this is being according to the sine wave, and this is the true value. So what will be the actual peak value of this triangular wave? So it will be 2.495 into 2. We will get that as 4.98 volts. Okay. Now, so this is actual value of this triangular wave, 4.98. So now, once we get the actual peak value of the triangular wave, so what will be the RMS value? RMS value of this triangular wave will be Vm by root 3. It is equals to 4.98 by root 3. So this will be what? This will be 2.87 volts. So now what does this answer means? So this means, so initially the question said it measured 2.77 volts. So we have this 2.77 volts, okay? But this is according to this sine wave calibration. So we did some back engineering. What we did, so we had this 2.77 volts, and this is what Vm by root 2, because this is a sine wave calibration. Based on that, we calculated, okay, what would have been the peak value which this calibration uh, did according to that, which is calculated 2.77. So the peak value it calculated was this one, Vm equals to this. So but this PMMC measurement, it gives average value. So based on this peak value, we got the average as what? 2.495. Okay, so this value was being calculated by what? This sinusoidal based PMMC measurement calibration. This thing. But now actually what we gave a triangular wave. So what is the average value of a triangular wave? It is the peak value of the triangular wave, that is Vm by, we can say Vp. Okay, this is different. Okay, this is Vp by 2, and it is actually equal to the PMC measurement calculated average value of the PMMC output, average value. Okay, this is equal to this. So we got the peak value of this triangular wave as this one. This is P. Okay, let's say P. So this we got. Now since this if this PMMC instrument average value would have been calibrated in terms of triangular wave in its RMS scale, so then actual RMS that it would have shown was Vp by root 3. Okay, and that would be 2.87. So what happened? We got display as 2.77, but we wanted 2.87. And why we didn't get 2.87? This is this is true value for RMS. Why we didn't get 2.87? Because it is being calibrated into in terms of sine wave. Okay, it might be confusing. If you will see this again and again, you will get to know what I'm saying. It took me also to grasp this thing properly. It may be confusing. Okay, but if you have any doubts, we can again discuss this in next session. No issues. But as you will solve more and more questions on this type of question, these types of questions, you will solve more and more, then you will get more clarity, and then these things will make sense. Okay, so but yeah, so just end we end this question. Percentage error will be what? So this is two true value, that is 2.87 minus actual 2.77 divided by 2.87 into 100 is equals to what? Mine plus 3.48%. Okay, no issues if you are not getting anything. Then also it's no issues. If you're getting something, also fine. And if you're getting everything, then it's perfect. But just go through again and again, because these type of questions, I think these are good for your understanding of how the instruments are being calibrated. And if in terms if we say in terms of like exams, then it may come in your gate exams also, as well as in this course also it can come. But it's always good to know, okay, so this is kind of a very practical questions where you can see, okay, if you are seeing any instrument and if you see, okay, it is being calibrated in terms of sine wave, so you should know like what does it mean. So what does it mean if you are giving any other signal, so it will give error, you should know why it is giving error. It is giving error because of all this theory which I just told you. Okay, so it is a good practice to know about the practicality of the systems. Okay, but just I will say just go through again and again, you will get to know. uh, so this another question is of the same type. So this I will give you, this I will uh, leave it for homework. Okay, and form factor, you know, it is vrms by v average. This is given. Okay, so so if you will see the answers for these type of questions in textbook or something, so people have done directly like using this form factor. But what I told, it is kind of more using basic ideas. But if you get so good in this, so you can go directly with this help of form factor. But once you should be clear with the basic thing, okay, then you can directly apply this form factor and you will be easily able to get these type of questions. Okay, so this I will give you homework. So in this, okay, the I'll just say the instrument is being calibrated in terms of triangular wave. Okay, oops, what happened here? So it is being calibrated in terms of triangular wave, and now we are measuring a sine wave. Okay, so this is a difference. Earlier, what happened? The instrument was being calibrated in sine wave, and we were measuring triangular wave from that. So now it's opposite. So just solve this thing, like apply this same thing what I did here, okay, to this question, and you will get to know. So I will, for your um, benefit or for your ease, I will just give you the answer for this. I think I have the answer. Yeah, so answer for this is 3.52%. So whenever you get time, just solve this, and if you have any doubts, we can discuss in next session. Okay, so now what is the next question? This is okay. Compute the value of multiply resistor for a 20 volt RMS sinusoidal AC range of voltage shown in the. Okay, I think we have done this type of already, but I wanted to tell you. Yeah, this one is fine. This is a full wave rectifier. Yeah, so this one. So this we have done already. This one kind of this type of question. This we'll see. So we have a rectifier type instrument, basic, so it uses basic PMMC movement of 100. So this means like this is a full scale deflection reading, full scale deflection value, and it is having a resistance of 2 kilo ohm. It employs a full wave rectifier circuit. It employs a full wave rectifier circuit with forward resistance of each diode being 2 kilo ohm. The reverse resistance of the diode is infinite, fine. The range of the instrument is this, sinusoidal. The resistance of the multiplier resistances. So I will draw the circuit for you. So in lectures we have seen this thing. We have what? Just to check the diode positions. Yeah, so we have something like this for a full wave rectifier circuit. We have something like this. Okay, and we have an instrument here. It's coil resistance here, and this is being connected. This is output. So this we saw in the class lectures, and this was the multiplier resistance. So this is PMMC, and we have, so this is PMMC meter, and we have this 500 ohm resistance. It is being, sorry, not 500, it is 2 kilo ohms. 2 kilo ohms. Okay, now so we have to tell what will be the this multiplier resistance if we give a 0 to 20 volt AC sinusoidal. So one thing to keep in mind, if nothing is mentioned, then it's RMS value. Okay, if nothing is mentioned in the question, then it is the RMS value. So just try to solve. So let's say, okay, I will give you one more help in this. So for positive cycle, what will happen, how the circuit will be looking like. So this diode will be on, and this current will go like this, and this diode will be on. Okay, so but now the diode resistance, what they have given, the diode forward resistance is 2 kilo ohm. It looks something like this. We have PMMC 2 kilo ohm, then we have another diode here. So these are open, these two branches are open. This is 2 kilo ohms, this is RS, and we have a signal exiting from here, this side. So it came like this, and went like this. Okay, so let's say this is RD, this is also RD, this let's say RC. So what is the total resistance for one cycle? It is RS, this RS, plus 2 times, because we have two diodes, 2 RD, plus we have one coil resistance RC. So this is the total resistance for one particular cycle. Okay, now question is saying we have to find this RS. So now we have inputted a sinusoidal wave of 0 to 20 volt AC sinusoidal. That means the amplitude of this is 20 volt, 20 root 2. Okay, because that is RMS value. So this is peak value of this thing. We have inputted this, so it will be full wave rectified like this, and the PMMC instrument will be calculating the average of this signal. So average is what? 2 Vm by pi. That means what is Vm? Vm is 20 root 2. Fine. So this is V average. Now we have full scale deflection also of this instrument. It's being given in the question. So IFSD, because they are saying we have to find RS such that if we give this much of voltage input to this circuit, then there will be a full scale deflection for this circuit. So this, since when they mention range, that means they are talking about the full scale deflection. Okay, so I full scale deflection, as I told earlier also, since we are talking about PMMC, this I full scale deflection is basically I average, which is being given here is 100 micro. Okay, and what is I average? I average is V average, that is the average. This is the average being seen, average voltage being seen by this PMMC instrument, divided by the total resistance of this branch. Okay, simple Ohm's law I'm using. RS plus 2 RD plus RC. So now what we have, okay, I don't have space. Hmm. Add one, yeah, okay, yeah, added. So we have I full scale deflection equals to I average equals to 100 micro. It's been given, and it is V average divided by RS plus 2 RD plus RC. So what is V average of a sinusoidal full wave rectified signal? It is 2 by pi to 20 root 2 divided by RS we don't know, RD we know that is 2 kilo, so 2 kilo, RC we know what is 2 kilo, 100 micro. So now uh, it's very easy to solve this thing. So RS will be just here and there we'll get RS as 174 kilo ohms. Okay, so these type of questions are also very common. Yeah, you can switch on a mic and you can ask.
Sir, there's a multiplying resistance.
Hmm.
Instead of multiplying resistance, in some problems they use multiplying capacitance also.
Uh,
Why? How capacitance will help in multiplying resistance, sir? Because we add resistance so that voltage drop increases.
hmm.
Like if we add capacitance, it will not.
Okay.
How it will?
So you are saying instead of this, we have something like this. Okay. So if we say for a voltmeter, if we have, let's say if we start with the basic voltmeter thing which we had. So if we add this thing here, so I will say since there is a voltage drop in that, and then this capacitor. So let's say instead of R, this is the series resistance. This is RC. This will be RC minus 1 by j omega c. Okay, if we calculate RC minus 1 by omega c square plus square. So see, when we calculate in one way we can say, okay, when we are using the series resistance here instead of capacitor, so what ultimately is happening, the resistance of that is increasing. Instead of RC we are having RC plus RS. Okay, but if we add a capacitance, so now since we are talking about capacitance, then we will talk about impedance. Then also the impedance, because initially what was the impedance? RC. Now we have next the new impedance is RC square under root of RC square plus 1 by omega c square. Then also it is increasing, so somehow we are increasing the ultimately the impedance of the this branch. So so that the concept is clear that okay, I think it's clear that we are getting more drop here by adding a capacitor here. Yeah, but I will definitely give you more clarity, and I will come with one question also if they are using any like capacitor in this as a multiplier thing. I will solve that. Okay, I will write here question solve any question on using multiplier capacitor in next session. I think yeah, this will clarify more like your doubt. We'll solve this in next session. I will find out one any question and I will solve this for next session. Okay. Yeah. This is one. So yeah, I think we are done with this. I think we are done with time also. So this was kind of, but this was only half a rectified thing, and you can see this question, and yeah, you can see this question and you can solve this also. You can, this also can be a homework for you, and this is basically not IP. This is input. Okay, and answer for this is Answer is what is the answer for this? Hmm. Okay, just you came come up with your answer. Okay, I have the answer. Okay, wait, wait, wait. 48 root 2 by pi. This is the answer for this. So just if you solve this, if you don't get this answer, then let me know. We'll solve this in next live session. And yeah, this thing we will solve this in next live session also. So I think we are done. So any other doubts apart from this? And one more thing, I will encourage you to be a part of live session so that it is better to see the live session instead of going for recorded session. Then you cannot ask questions in between. And yeah, and it will be a good motivation for me to come with more good questions for you. Okay. So that is one request. Apart from this, fine from my side. If any questions from your side, you can ask me right now. You can type in discussion forums also. We will be happy to solve there also. Yeah. If no questions, yeah, you can leave also. Thank you for being part of this live session. We'll meet next week, Tuesday, this 6 to 8 p.m. Okay. Yeah. Thank you. Yeah. Welcome.